SID is double. This is in generality. If it's double, the same number of photons is spread over an area 4 times. Therefore, it's going to be a fourth of its original intensity. If I were to triple my SID, my beam is reduced to how much now of its original intensity?
Third?
Well, yeah, because we're squaring it, right?
Oh.
So it's going to be a what? You
1/9.
said it, a ninth. It's going to be a ninth of the original intensity. Right? If I quadrupled it, what is it going to be?
1/16.
1/16 of the original. See that? You guys follow? All right. So the new formula that we're going to be learning here is what's known as the inverse square law. And it's written like this. It's inverse because you're going from the original intensity over the new intensity is equal to the new distance squared over the old distance squared. And our answer is going to be in Roentgens. Our answer is going to be in Roentgens. Let's apply this to a real situation. Here's the inverse square law. An exposure is done at 40 inches. SID. What's SID? Source
to image distance.
to image distance. The distance from the X-ray tube to the image receptor. An exposure is done at 40-inch SID. At 40 inches, an ionization chamber measures the radiation exposure of 5R. Okay, so at 40 inches, we've got a Geiger counter, and it's measuring 5R coming from that radiation source, 5 Roentgens. What will the new reading show me if the same technical factors were used, the same amount of energy was being emitted, however, at a further distance of 45 inches? Do you think it's still going to be at 5R? Okay, I'm going 5 inches further away. Is it going to be the same intensity?
It's going to be lower.
Probably not. Yeah, by just what we know, it's going to be lower. Everybody agree? All right. So this is the inverse square law. Because you're going old to new, new to old. It's inversed. Okay? Old intensity over new intensity is equal to new distance squared over old distance squared. Okay? But they're opposite. Okay? So it goes old to new, new to old. I'm trying to teach you guys how to recognize patterns. Old to new, new to old. All right? Let's plug in the numbers. Old intensity is 5R. We're looking for the new intensity. Okay, because we're looking for the new reading. The new intensity is equal to new distance squared. That's the new distance we're going to apply this formula to over the old distance squared of 40 squared. Okay? Before you cross multiply and divide, square your distances first. Square them first. If you don't square them first, you're going to come up with a completely different answer. I'm going to have to mark you wrong for it. I hate doing that.
Couldn't you simplify it first too, though, and then square 'em?
What's that?
Simplify the 40 and 45 and then square 'em?
You can do that.
Make it a little easier.
Sure. Whatever you
Yeah.
want to do. Yeah. Okay. If you know how to simplify, go for it. I don't know how to simplify. I'm very complicated. All right. So square of 45 is 2025. Square of 40 is 1600. Cross multiply. Now you can cross multiply and divide. 5 times 1600 divided by 2025 will give you 3.95 R. Okay? So at 45 inches, I'm a little bit further. The reading that I'm receiving now is going to be 3.95 R. Okay? What I do want you guys to tie this in with is when we're talking about the inverse square law, we are talking about things that are inanimate, something not living. Because we're talking about the intensity or the exposure rate coming from a radiation source. All we're trying to determine is the amount of exposure that radiation material is emitting. Whether it be the X-ray tube, whether it be a nuclear plant, whether it be a piece of fruit that got exposed to radioactivity. You understand what I'm saying? Okay, we're trying to determine the exposure that's coming from the radiation source. This is it right here, coming from the radiation source. So here is an X-ray that was done at 40 inches. Okay, we did it at 80-inch SID, so we're double our distance. And because we double our distance, okay, same amount of energy being spread out. It's not going to be as intense. This is going to be your resulting image. Now, let's apply the same concept here, but with live people. Because this is where I need to apply this concept to a real life situation. So knowing what I know, that if I'm closer, beam's going to be more intense. If I'm further away, my beam's going to be less intense. In real life situations, this is going to happen. You may have to do an X-ray, not only in the radiology department, but you may have to go to the operating room. You may have to go to the intensive care unit. You may have to go to the emergency room. You're going to be dealing with different environments and different factors. You're not going to be having the same old nice, room wherever you go. You're going to have a portable unit. You may have to go to the emergency room, and now you're dealing with a patient who can't stand up for you, and you have to take the X-ray on the bed. All right? And because it's the size of the room or the height of the gurney or the bed that they're in, will also change your SID. Are you guys following me with this? Okay, so the factors and the environment can change. So you're not always going to be working with 40 inches. You go to the ER, you may be dealing with 36 inches. You go to the operating room because there's doctors and equipment around. You want to bring your tube a little bit farther so you don't contaminate the operating field. So you're doing it at 55, 60 inches. Okay? But it's going to change. And with all the changes in distances, you need to know what kind of modifications you can do with your technical factors to make sure that your density stays the same. Because what we know is the further you get, the less intense it is. So that's telling me I need to bump up my technical factors. If I'm closer, it's going to be too intense, so I have to decrease my technical factors. But by how much? Okay? The direct square law. This is the direct square law. New, old. It's direct. New to new, old to old. Okay? So instead of intensity, we're going to put in place mass. So our new mass over old mass is equal to new distance squared over old distance squared. Because what we're trying to manipulate here is our technical factors, right? All right. So the direct square law, here, a technologist performs a chest X-ray using 3 mass and 75 kV at 72 inches. This was done in the department. I got my 72 inches. It was perfect. And I know that technical factor, those sets of technical factors will work at 72 inches. However, sometime between when the patient was admitted and got really, really sick and then got sent to the ICU, now the patient can't come down for an X-ray. I have to go shoot an X-ray portably in their bed. And due to the environmental circumstances, I can only get 54 inches. I can't get my maximum 72 inches. I'm going to be doing a lot closer. So if I don't adjust my technical factors with the change in distance, my film is going to be too what? It's going to be too dark. So I need to cut my technical factors to accommodate for the closer distance. All right, so let's plug this in. New mass, this is what I'm looking for. Old mass at 72 inches, okay? And this is the distance, my new distance squared. Again, square them before you cross multiply and divide. Okay, once I solve for x, at 54 inches, I'm going to be using 1.7 mass. 1.7 mass. Makes sense, right? I'm closer, so my technical factors should be less. This applies to the living, okay, or the object being X-rayed. This applies to the living. So if you get questions like this, try to determine, is it a patient that's being exposed, or am I just trying to determine the amount of radiation that's coming from the source? Okay? This applies to the living. Again, just a depiction of what happened. My original technical factors at a known distance. Okay. Patient got admitted. My X-ray tube was closer, but I didn't adjust or accommodate for the closer distance, so now my image is dark. So all I had to do was apply the direct square law at a closer distance, and now it looks as good as the original. Okay. All right. If I were to give you a set of factors like this, knowing what you already know about MA, time, and distances, will you be able to tell me which of these factors or combinations is going to give me the most density on my radiographic film by just simply looking at it? Could you? So there's a method to this. Let's do this. All right. First we got to do here is we got to assign a rating. Okay, I've got 4 combinations here. Let's just do a rating of 1 to 4. Okay. You can do 2 to 5, you can do 3 to 6, you can do 0 to 3. Okay, it doesn't matter, just as long as you know what your numbers mean. All right, 1 being the worst, or in this case, let's do the lightest. 2, 4 being the darkest, the most dense. All right, what do we know about MA? High MA or low MA is going to give us increased density.
High MA.
Does everybody agree? Mm-hmm. Okay, high MA. So let's do this. Which is the highest MA?
403.
Okay, so let's do, what?
Number 3.
Number 3, okay. So there's 4, 3, 2, and 1. Do we all agree?
Mm-hmm.
Okay, what do we know about time? Short time or long time?
Long time.
It's going to give you more density.
Long time.
Long time, okay? What I like to do is, you know, when I'm looking at it like this, it drives me all crazy, so I like to add zeros so that all the numbers look the same. So, let's just call that 10, and the 1 is 20. I mean, it's still the same number, right?
Mm-hmm.
All right. So, which is the longest time?
2.
Everybody agree? Okay. So this is 4. What's next?
3.
1,
Mm-hmm.
2, and then this being the less, okay. And then SID. Do I want to be closer or further away to give me more density?
Closer.
Closer, all right.
Number 3.
4. You gotta stand back. 4, 3. Does that look right?
Mm-hmm.
All right. Let's just add across. Let's total it. Tally it. What is this?
8.
6 equals 8.
7.
7.
11.
Is it really 11?
Mm-hmm.
Yeah.
Mm-hmm.
8, 9, 10, 11.
Okay.
4.
And 4. Which is going to give us the most density?
Number 3.
Do we agree? Number 3. So 400 MA, 0.1 seconds, 37 SID is going to give us the most density. Now, what if my question said the least amount of density?
Number 4.
Okay, after we figured it out, we should be able to know which one it is now, right? So yes, number 4 is going to give us the least amount of density. Read the questions closely. Oh, those numbers. Perfect. I always forget they're up here. 8, 7, 11, 4. Okay. All right. This is what we're going to do. We're going to stop right here.